Hi, I'm your Fisher LP application engineer Fernando, and I'm here to talk to you about the 63EG principle of operation. Now, if you've seen our previous videos, you know that the 63EG is a relief valve used to provide overpressure protection for LP gas tank applications. You may also know that the 63EG uses a dual pilot assembly to perform its relief mechanism. But what you are probably used to seeing out in the field is the multi-port manifold that uses 4 relief valves, 3 active, 1 inactive, in order to provide overpressure protection for these tanks. Now, the point of today's video is to go over how the 63EG works, hence principle of operation. Without further ado, we move on to the animation of the 63EG.
Pictured is the cutaway animation guide for the 63EG LP. We start first with the bulk storage tank. And it shows the 63EG mounted on top of the tank, which pictured here is the main valve. And this is exactly representative of what you would see in the field. Now, this main valve is normally closed during normal operating conditions. As you can see, this spring uses its force to help keep the seat closed onto the orifice. We move now to the pilots. You can see pictured here are 2 pilots, hence dual pilot assembly. Now, these pilots are also connected by 2 switching valves, which are controlled by this handle. The handle points towards the inactive pilot. So pictured here, this pilot would actually be inactive, whereas this pilot would be active. Now, if you look closely at the pilots themselves, you see here denotes restricted orifice. This is a constant bleed. It's a small bleed, which means if you have pressure coming through here and this pilot is closed, you will still have a constant bleed into this space. Now, the pilot itself is normally closed. Now, when it opens up a little orifice in this area that is bigger than this small restricted orifice and will actually allow pressure to evacuate. If this pilot is closed, as it will be in normal operations, you'll get a small bleed into this part, going into this switching valve, and bleed into your spring space. Again, this valve is normally closed under normal operating conditions. If you have tank pressure in this space, also on the top, this spring gives you extra force to keep this valve closed. This animation shows the tank and valve pressurized. And we will begin first with describing the coloring scheme for these pressures. Any pressure in red represents tank pressure / inlet pressure. In other words, this red pressure is exactly the same pressure inside of your tank. Any pressures in green denote the loading pressure when relief valve is open. This pressure is significantly lower than your tank / inlet pressure. Last but not least, pressures in yellow denote the atmosphere. I next direct your attention to your right pressure bar. You can picture this as a gauge. Basically, what we're going to show here is going from low pressure to a higher pressure, and we're going to put our set point, our pilot set point, somewhere in the middle. And we're going to denote what happens when you're below set point and when you're at and above the set point. Now let's look at the animation a little bit more closely. I want to direct your attention to the position of the handle. The handle is currently pointing to your right pilot, which means the pilot to your left is active, thus why you see it colored. Now, because this red pressure denotes inlet pressure / tank pressure, what we can see here is this sense tube is going to take that inlet pressure, move it into and out of the switching valve to your active pilot. And remember, This pilot during normal operations is closed. And I mentioned previously that you have a small bleed, an unrestricted small bleed, which shows here that pressure bled from this into the second switching valve, out of the second switching valve, and into your spring space. Also notice on the pilot that this inlet pressure is being directly sensed under the pilot diaphragm. So once pressure gets to the pilot's set point, it's sensed directly under this diaphragm, and it begins to start to discharge and open up this mechanism. Again, this animation shows the valve when it is normally closed and it is under the pilot's set point.
Now you may be wondering, how exactly is this pilot going to make my main valve respond and relief in the event of an overpressure situation? Well, let's go back to our animation.
We now go over the 63 EG's relief operation. We will build pressure up until pilot set point, and in fact over the pilot set point, and see how the pilot reacts. So as we start to begin to build pressure, once it reaches the pilot set point and builds pressure above, you now open up the pilot and allow this pressure to evacuate. In other words, in an overpressure situation, you will be relieving through the pilot. As you can see, because you are relieving pressure, this green pressure is much less than your inlet/tank pressure. And this allows the pressure to overcome the mainspring and allow the seat to come off the orifice to allow for full relief to the atmosphere. In summary, the pilot is what's controlling the main valve. And as you build pressure right under its pilot's diaphragm, it allows the pilot to open, hence open up the main valve.
What you're telling me is that now I'm fully relieving. But how exactly do I get the valve to reseal? You guessed it. Animation?
Shown in the animation is the 63 EG under an overpressure situation. In other words, relieving from the tank to the atmosphere. Now what's important to us is how does this valve reseal itself? So we'll go ahead and take pressure down to and below set point and see how the pilot reacts. As you can see, the pilot now shut itself off and did not allow this bleed to go out of the orifice, and you still have that small restricted bleed, so you just refill up this loading pressure with tank pressure and allow the spring to overcome once again and shut the main valve off, thus resealing your valve and not allowing tank to bleed into the atmosphere.